Okay, recording started. So I thought that I could talk about the following topics today. So elaboration and unification with sigma types. And like some extensions of unification which handle sigma types in a better way, and also maybe some questions or design decisions about record types, like how to support record types and like native record type versus like record types just as a sugar on the top of sigma, and some questions of generativity of record types and stuff like that. Okay, and I made a little implementation which is not so I made a new package in elaboration zoo which is currently called sigma unification, and I will push it, but it contains some enhancements of unification with sigma types, but not all. So in elaboration zoo right now we have unification with sigma with I don't know like how strong it is compared to Agda, but I would guess that maybe 80% of Agda extensions, 80% of unification extensions related to sigma is included compared to Agda. Okay, and the reason is that I know how to do this part very simply, but the remaining 20% I haven't yet figured out how to make it nice and efficient. But I can talk about this in detail. Okay, so let's do sigma types. And what kind of problems do we have with sigma types in unification? So let's just assume that in the surface syntax I have something like x, a, b. So this will be the syntax for sigma types, and we can also do some nesting of this operator. So we can do x, a, and then y, b, and so on. And we can also have pairs. So this is the syntax for types, and this is the syntax for pairs. And pairs can be also nested, like t, u, v, so on. And then probably you can guess that what I'm doing in the elaboration package is actually some kind of syntactic sugar for treating iterated sigma types as records. Okay, and then we also have projections. And projections look like t.1 or t.2, or actually we can also have t dot and then some kind of name. And the way it works is that so named projection is also just a syntactic sugar on some kind of iterated projections. So it's a sugar on iterated projections. So if I can define something like a category would be an object, and then some morphisms, and then we can skip the rest of it, but with this we can already use a named projection. So if I have ccut, then I can do, maybe let's just write an example like this. So from cut I can return something. So from a cut I can return a c-obj arrow u, and I can define it as a lambda c.Mor. And then actually in the core language, so in core syntax, the named projection appears as a primitive operation. So named projection is primitive. So it doesn't disappear, and the reason that I don't want the named projections to disappear because I want to print it back as the user wrote it. So because we want to print it back. And it would be very ugly if I'm having a big record and I'm writing a named projection, but then it just gets unfolded to like a .2.2.2.1 or something like that. But the unification kind of unfolds the named projection. So the unification immediately unfolds the named projection to some iterative projection. So it's transparent to unification, but it's relevant to printing. Okay, but if we have this, then what issues do we have in unification? So previously we had the pattern unification. And in pattern unification, if I have something like an alpha applied to spine, and I want to unify it with the right hand side, and then this only works if I have the spine only contains some x, y, z, etc. So only bound bars in spine. So in pattern unification, only bound variables are allowed in spines. However, now the spines do not only consist of applications. So spines also have projections. So now I see that a spine is defined not just as a list of values. So previously a spine was just a list of values, and then every entry just represents a function application. But now a spine is more convenient to be defined as some custom data type. So it can be an empty spine, or it can be an application, and then we have a spine and some value, and in the actual implementation we also need the isitness of the application. So this could be implicit or could be explicit. And we also have projections. So we have a first projection, and we have a second projection, and we also need the named projection, which I called field, and then the field projection is just a string for printing purposes. So there is a name, but there is also an integer, and the integer just represents how deep we go into some particular right-nested sigma type. So I should also mention this, is that a named projection it goes into a right-nested sigma type. So every named projection looks like how does it look like? So it's basically its second projections, and then at the very end we have a first projection. So if we have a t.2.2.2.2.1, so this would go into right, then right, and then take the first component of a sigma like this. So for example, if I'm having this category, then the c.obj is the same by definition as c.1, and then the c.Mor is the same by definition as c.2.1. So we always have a 1, but then we can have an iterated second projection before this first projection. Okay, and now the spine looks like this. And in the values, so in the val, we have flexible, and we have the rigid neutrals. And the flex, it has a meta variable, and it also has a spine, and the rigid one has as a bound variable and also a spine. Okay, and but then the question is, so why do we need to have projections in spines? So what happens if projections are not in spines? So how could that be? How could we implement that version? We can say that the spine is just as before, but the value is has an extra constructor for the neutral projection. So we can say that a value can be approach 1 of a value, or it can also be approach 2 of a value, and so on. But this is not very nice, because if we think about unification and forcing as well, so unification plus forcing, the point of having this setup with the flexible and the rigid neutrals is that we want to immediately get access to the reason why some particular computation is blocked. So we want access to the reason why computation is blocked. And if we have a core language such that the only way of doing beta reduction is function application, then the only way computation can ever be blocked is by having either a meta variable or a bound variable and then doing some number of function applications to it. So in that case, this is the right representation, but now we also have beta reduction of projections. So now it really makes sense to extend the spine with the projection and not the value with the projection, because if we do this, then we are not able to immediately access the reason of having a blocked computation. In this case, this could be like an iterated projection, so it can be a v-proj of a v-proj of a v-proj of a v-proj of an application of a meta var. But what we are interested is the meta var. And then we have to dig inside this expression and get out the meta var. So it's not very convenient. And if we think back to forcing, so in forcing, so we want to just immediately mention a flex, and then if we have a flex of a meta, then we can just immediately try to restore the computation. So the spines only get more complicated from this. If we have inductive times, then the spines should also include eliminations. And if you have more complicated computation, then the spines become even more complicated. Like for example, if you want to do setoid type theory or cubical type theory in a more principled way, then the spine becomes like a lot more complicated, because then the spine represents any kind of blocked computation, and setoid or cubical type theory has more complicated and more kinds of computation. So we have like computation of transports, computation of certain operation on intervals or whatever, and then we also need to represent a blocked computation using the spine in some way. But now it's still pretty simple, so we only have projections and applications. Okay, so but let's go back to pattern unification, which we kind of we went into a tangent. So pattern unification, we still only allow bound variables in the spine. So now we still only allow bound variables. And there are some papers about extending, so there is some work on extending pattern unif to projections and pairs, but I don't know, I never read this work. But instead, so maybe you can look it up, but the approach which I am using is so this is the solution which is used in the solution, and you can also find it in the higher order unification paper. And the solution is just to get rid of all of the sigma types. I mean, just get rid of sigmas. And how can we get rid of sigmas? And conceptually, the way it works is that there is some syntactic translation, or there is some model of type theory. There is some translation model of core TT, which essentially it eliminates every sigma. But of course, it is not literally possible to just do a translation from a type theory with the sigmas to a type theory which does not have any sigmas. But instead, what happens is that a sigma in the core syntax instead becomes a telescope in the meta theory. So sigma in syntax gets converted into a telescope in the meta theory. So for example, like what happens if I have a function which goes from A to B times C. So I have a product here, and I cannot translate this term, or I cannot translate this type to something which is again just a single type and it doesn't have any sigmas inside. So instead, what happens is that I get a telescope in the meta theory. So I have an F0 which goes from A to B, and then I have an F1 which goes from A to C. And this is relatively easy to do if we have meta variables. Like for example, if I have a meta variable which returns in a sigma, then it is possible to do an eta expansion of a meta, which immediately solves this 0 with a lambda a dot, and then we have a pair here. So we can just do an eta expansion, and the eta expansion just goes along pi and sigma eta. So this is some kind of type-directed operation, and we take one type. If it's a function, then we immediately insert a lambda, and if it's a sigma type, then we immediately recursively continue the expansion inside these pair fields. And whenever we hit something which is neither a pi type and neither a sigma type, then we just insert a fresh meta. So if type is not pi or sigma, then we just insert a fresh meta. And this insertion of a fresh meta is kind of extends the meta context, and that's why you can think about it as a meta theoretic telescope. Okay, so in this case I had 0, but now I have 1, and I also have 2. And this is just solved with 1a and 2a. Let's swap it. And 0 still has the same type. So, I mean, just as with pruning. So with pruning, I'm giving a prune solution for a meta, but everything has to preserve the type of the existing meta. So the existing type is the same, but I have an immediate eta expanded solution for 0, and I also have a function like this, and I also have a function like this. And these methods are still unsolved. So this is one thing which we can do. So one thing is kind of eta expansion of methods. And this can be used for a number of purposes. So this is just a quick example. So this can be also used. So in Agda, whenever we have a function, so if I have a function which goes from, for example, a top type to something, and then if I'm writing this, then actually if I am only following the bidirectional elaboration, so if I'm only following the bidirectional elaboration algorithm in like in all the previous elaborations of packages, then if I'm writing something like this, then this never gets solved. And even in Agda, this whole would never get solved without this eta expansion of methods. Because there is no unification constraint involved here. So here we generate a meta, but because there is no constraint, so no unification involving the whole, so the meta never gets solved. And the way that the meta can get solved is that we use this eta expansion of unsolved metas at some point. So we use eta expansion at some point. For example, we can use eta expansion when we are creating a fresh meta. So we can immediately eta expand on fresh meta creation. So we say that instead of just inserting a new meta with a particular type, we say that we create a fresh meta. We create a fully expanded meta of the given type, and then that's just a fresh meta. But I don't think that's a very good idea. So I think it should be avoided, because this eta expansion can create like lots of metas. So if we have large records, or if we even have like nested record types or nested sigma types or functions returning nested sigma types, and if we immediately do this eta expansion, then we are going to get like a whole lot of fresh metas. There is a question, when is 0.5 in the chat? So but maybe Ochars would want to join, and I think it's okay. I think we can continue. Yeah, so it would be a valid thing to do, to just immediately eta expand when we are doing a fresh meta creation. But I think it would be probably not efficient enough, because then we get lots of metas. So instead, when do we eta expand? So we only do this eta expansion. So we expand if unification, if pattern unification fails on a projection in spine. So if we have something like 0, and then we have maybe this is applied to x, y, but then we have a projection, and we want to unify this with the array address. So if we get a projection here, then actually we know that that after we eta expand this meta variable, then all projection must actually disappear. So it is not possible that we do an eta expansion, then we solve this 0 with the expanded version, and then after we solve it, then there cannot be any projection here. Because if we have a projection, then we know that 0 is a function which gets one argument and another argument, and then returns a sigma. And the sigma is going to go away when we expand. So after eta expansion, instead we have like a 1 xy. So after eta expansion, we have that the 0 is solved to be lambda xy dot 1 xy and 2 xy. So we split 0 into two meta variables. And now the thing to note is that this unification problem, when this unification problem is solved, we are creating two new metas. So two new metas, and only one is solved. So you can view this as a partial solution. So if you have a problem with the projection, then of course what happens is that only part of some record is determined by the problem, and all the rest, that all the other fields of this record are completely unconstrained. Okay, maybe not completely, because there could be some type dependencies, but usually it's not fully constrained if you only know what the projection of a particular expression is. So we create two new metas, and we solve one of the two new metas. And this is fairly simple. And so if we have this kind of solution, we still do not have, so we still do not reproduce the Agda feature that whenever we have a hole with type unit, then it always gets elaborated to just TT. So we still do not get this kind of feature, because we can still get that if there are no unification problems related to this meta, then we never get to know anything about this meta. But we can still do that that maybe unsolved metas are, so we can just try, so we can try to eta expand unsolved metas. This is one way to do it. So we do some elaboration, then when we feel like it, we can try to eta expand unsolved metas, and sometimes it helps and sometimes it doesn't. But of course this is kind of there are a lot of choices. Like at this point we are doing like this speculative computation, which is very, very common in Agda, and which is very, very common if we have constraint postponing. But so this is kind of the point where the evil of constraints and constraint postponing kind of enters the picture, because previously everything was just completely deterministic without any kind of postponing. but this is something that we have to embrace. So after some point, if we want to get new functionality and we want to have stronger elaboration, then we kind of have to make peace with all these like tremendous like design choices and kind of degrees of freedom in postponing and retrying things. Okay, so this was eta expansion for metas, and it's pretty simple, but it's not the whole story. So eta expansion is not the full solution, because we can also have like things like sigma projections and like pair constructors. So we can have projections and pairs inside spine, meaning that that we have some application in a spine. So some application in a spine which contains projection or pair, and this is also not covered by the pattern unification. So if I have this, and then maybe I have a meta variable which is applied to a pair, or maybe I have some meta variable which is applied to a projection of something. So maybe like this, because this eta expansion of metas, it only handles the cases when the spine itself, so on the outside we have a projection. So the meta variable is the thing which gets projected, but here these are the values, like the values in the application which get projected, and we also want to get rid of these. Okay, and how can we get rid of these? The way we can get rid of them is, and now let's be a bit more kind of formal. So a bit more formally, essentially we are using two definitional equivalencies. So two equivalencies, and the first one is just currying. So we have currying, which says that if I have an x such that, so there is a function which has a sigma argument, and then we return in some type. So here we have a pi of sigma and something. It will be a pi of sigma a b c, and then this is equivalent definitionally. So, and by definitional equivalence I mean that there is a function which goes one way and a function which goes back, and if you compose them, then they are definitionally the identity functions. So this is isomorphic to xa, or maybe aa bb arrow of c, but here we have some substitution because the x should be ab. So we have this dependent currying isomorphism, or like the defining isomorphism of dependent function types, and then we have the so-called type theoretic axiom of choice. Which means that if I have an AA which returns in a B b times c, then this is also definitionally equivalent to having now a function. So here we have an existential thing, but the existential thing is raised, so it and becomes a function. So it becomes function which goes from a to b, and then we still have the c part of this, so we can go from a to c of a of yeah. So a is the same, but b substituted to be b of a. Okay, so we have this kind of equivalencies, and essentially what happens is that we are just using these two equivalencies to rewrite from left to right, and we just do all of these possible rewrites. So for example, if I have a function, or if I have a type which goes from a to b to c, then as I mentioned before, that so here everything is internal, but we can see that the sigma moves out if we are using this time theoretic axiom of choice. So in the end, every sigma basically, so every sigma moves to the top level, and you can also view it as Scholemization. So all the existentials move to the top. So this is exactly the type theoretic version of Scholemization, or also the type theoretic version of lambda lifting. So if we have this A arrow BC, then it becomes two functions. So if I have some function which goes from A to B, and also some function which goes from A to C. And it can be a bit more complicated, because we can also have like an opportunity to do a Scholemization in the argument type of a function. So if the argument of the type of a function looks like an A arrow B times C, and then we are returning to D, then we can also eliminate this product here by first doing it like this. And then we can use currying to get this. So this one would be like a Scholemization, and this would be currying. Or it's probably shorter to call it axiom of choice. And then if I have so now if I have a spine like a 0 is applied to, maybe the simplest case is when we only have to do currying. So if 0 is applied to just a pair of xy, then after we do this transformation, then we will get xy. So this would be like a currying. But we can also have, okay, so what is an example when we want to eliminate some projection? So what if we have x dot 1, and then this is goes together, okay, then what happens is that we have a meta which depends on x, but x is a product, or x is a sigma. So, but the new meta is not going to depend on a product. So because we can just use a simple currying. So if we assume that okay, so sorry, this is not currying. Yeah, but okay, this is currying. Okay, let's just write out the times, because I get confused if I don't write it. So this goes from A product B to C. Yeah, so this is well typed, and then we have a 1 which goes from A, B, C. And here we have a 0. Okay, maybe it makes sense this way, because so every meta variable has a closed type. So if I'm using, so x is a bound variable, and I'm using add x.1 here, then one specific specific case when this makes sense is that when I have some A product B, and then some A, and then some C. So here 0 is applied to this, and then it's also applied to some projection. And after I do this reduction, what happens is that I get an A, B, A, C. And then this becomes essentially x0, and then x1, and then x1. And you can see that here the bound variables themselves get kind of split up. So the bound vars also get split up in some ways. Okay, but I think an intuitive explanation is that if I have a meta, it's always something closed. I mean, at least in this particular setup where we do not have precisely scoped metas, every meta is completely closed. So if I just so what I can do is that I have this meta, and then I transform the type to some A prime, which is kind of the sigma eliminated version of A. So first I can do this, and then I can create an inhabitant of A prime by creating an eta expanded meta for A prime. So I mentioned that whenever I create a fresh meta, I can always just create a fully eta expanded version. So I can create some fresh meta which has type A prime, and which is fully, okay, this is not actually meta, but it's a term, but it's a term which can consist of like many metas, because if it's fully eta expanded, then it's eta expanded to like lots of metas. So we create a fresh term which is fully eta expanded, and then this is a kind of a complicated part, because I have to solve 0. I have to solve 0 with something. So I have to solve 0 with something which has type A, but I don't have an inhabitant of A, I have an inhabitant of A prime. So if I want to do this solution, then I have to somehow transport. So we need to convert or transport, and the transport is actually probably a good word to use here, because we have an isomorphism between A and A prime. So I have to transport the A prime back to A, and then I can solve this with kind of a transport of So if you want to do this like fully, so if you want to do the currying and the axiom of choice and everything here, and it becomes quite complicated, because not only do we have to create the new type, but we also have to, in a kind of a mutual way, we also have to show that this is an isomorphism. So what we are doing is kind of returning an isomorphic type. And there are probably many ways to do it algorithmically and many ways to formalize it. I'm not sure if this is the simplest version, but this is the simplest version which I currently know about. So formally it would look like if I have a type gamma, then from a type gamma I want to return some A prime, which is also a type gamma, such that there is and here I have a bunch of different choices. I could say that there is an isomorphism of A and I prime, like an isomorphism of types. But alternatively, it should also work to say that, that I want to convert the context as well. So we say that if I have a context, then from this I want to compute a gamma prime, which is also a context, such that gamma is isomorphic to gamma prime. And this isomorphism here would be a pair of substitutions. So it would be a pair of environments. And at the same time, I want a type in gamma to be converted to a type in gamma prime together with a proof that A is isomorphic over this isomorphism. So here I have to use some let's name it iso gamma. So this is isomorphic in a dependent way over the context isomorphism to A prime, and then T and gamma A and so on. So I'm sure that there are like a bunch of different ways to make this formal, and definitely, so I think the two main choices: do we only want to convert a type to a different type, but leave the context alone? So the first version is only convert types but leave context alone. And the other choice is to convert everything. And here, if we also want to convert context, then we need to do this conversion that whenever I have a gamma, so add the following. So we also have then currying for context, which says that if I have a gamma and then an x in A, B, then this gets converted. So the context already gets converted to a curried version of the same context. And I'm not sure which one is more practical. So I've only implemented this version. So what I implemented right now. So I implemented the version when I only convert types. So only convert types, and also I don't actually support this axiom of choice. So I only do a currying and then I do the eta expansion of the resulting types. So I only convert types and only do currying in a kind of shallow way. So because I only have a shallow kind of currying, it is possible to do. So one example which works is that I have an A, B, maybe C, D. And then this gets converted to an A, B, C, and also another meta variable which goes from A to B to D. So this is kind of a shallow currying, and so this works in my implementation. And what does not work is when I have something like A arrow B, C, and then D, and then I want to convert it to A arrow B. So this does not work, but in practice this works for many interesting examples. So if you only have this currying and only have the eta expansion for methods, so the eta expansion can essentially do this axiom of choice transformation, but only for the return type of a method. So if a method goes into some kind of product type, then we can expand that, but we cannot do an expansion in a nested way inside the function arguments. And this works for many practical purposes. Okay, at this point I think we can look at the implementation, and then I can also do some explanation, like what was the reason that I only implemented now the currying, and with this kind of translation that I only do a type conversion but not a context conversion. Okay. Okay, so first let's look at the syntax. So it's pretty much the same. We have sigmas, and we have pairs, and we have first projections, second projections, and field projections as well. So this is the name of the field, and this is like how deep this field projection is. So this int can be unambiguously used to convert a field projection to an iterated usual projection. So this is the syntax, and then in values we have the change that the spine is now defined like this. So we have application, and then we also have projections. Okay, and now there is another change here, and the other change is now I say that the closure can be either a first order closure, so first order closure, which is the close, or it can be a higher order closure, which is the fun. And what's the reason for this? So previously I mentioned that usually the first order closures are more efficient, but here we already have this currying operation, and the currying is very convenient and also quite efficient to do with higher order closures. And I think this is like the first example where we want to do some non-trivial kind of transformation on values. And non-trivial transformation means that we actually have to implement this translation of a type to a curried type, and we also have to translate a term with a curried type to a term with a non-curried type. So this is some slightly more complicated operation on values. And here it will be very convenient that we have this fun with this higher order constructor. And in setoid type theory, we have this all the time because we have even more computation which involves like shuffling structure around and also moving binders and variables around in different ways. And if we want to do it with closures and terms, then it becomes a bit like it's very painful because we have to use De Broglie indices everywhere, and we have to implement substitution and renaming and weakening and whatever. So it's very annoying. And like a big advantage of using higher order abstract syntax is we can just forget about the context. So we can completely ignore the context and just pretend that all of these kind of all of these values with the higher order closures inside are just some kind of values free floating, and we don't even have to know about what the context is. But then the disadvantage is that some kind of transformations are just not possible with higher order abstract syntax. So when it works, then it's very good, but sometimes it does not work. And the reason that I only have currying right now, because currying works in a simple way with higher order abstract syntax, but the axiom of choice doesn't, unfortunately. Okay. So what else do we have? In evaluation, so in evaluation there is some new stuff. So in evaluation we have to handle the higher order case in closure application. So now we have like the usual case, and also whenever the closure is just a function, then we apply the function. And then we also have to implement the semantic version of projections, but it's quite simple. So the first projection just performs first projection, second projection likewise, and the field projection does some recursion on this int index. So it goes inside a canonical pair, and otherwise we just return a neutral expression. Okay. Yeah, but what about unification? So we have the new stuff in most of the new stuff in unification. So now in unification, so here we have the currying. And you can see how the currying works. So there is this function curry, which I simply type annotate it as something which goes from u to u, and the reason that I'm giving this kind of naive type annotation is because I don't have to care about the context because of the higher order abstract syntax. So I can just completely ignore the context in this case. And then you can see that the way currying works, so this is some kind of U pattern abuse, but what happens is that if I have a pi type such that the domain is a sigma type, then I just return the pi type. So I return a pi which goes from A, and then I can immediately use this function constructor for the closure. And then I have to do a currying recursively, so maybe it makes sense to just write this out in a more readable way. So if I have a curry of an x of a times b of a, yeah. Let's just pretend that all of these b's are functions as well. Okay, and it goes to c of x. Then this is defined to be a arrow curry of b in ba to c in a pair b. Okay, so this is how it works, and of course we have to recursively go one step deeper into the function type here, and this is exactly the same. So a pi of a sigma returning a c is converted to a pi of a, and then a curry of a pi of b of a, and then a c is applied to a v pair of a b. And it's an interesting homework to try to do the same thing but with terms. So implement or implement the same thing but not with terms but without fun. And So if we don't have fun, then it is no fun. So the implementation is no fun if we don't have fun. Okay, and otherwise we are just returning the type unchanged. And we also need, actually we only need one part of this isomorphism. So we only need to be able to convert from a value of query A to A, because as I mentioned before, we are creating something, some eta expanded term of meta variables which has a query type, and then we want to convert it back to a non-queried type. And it's pretty much, it follows the same pattern. So, but here we also need to take the A as an argument, because the computation on terms has to follow the computation on types. So it's still type directed, so we cannot just do a pattern matching on T, because it depends on the computation, completely depends on the types. So if we have the case when there is actually a querying, then what will happen in the end is that the T is mapped to lambda AB dot from query. Essentially it gets mapped to this. So the from query still takes a type, and we are querying the T applied to the first argument, and then we applied the T to the second argument. So if you look over this, then probably it's correct, and it works as intended. And this is not very nice. So if you look at this expression, then it is quite noisy, but this is still a kind of a shallowly embedded way. So if I have to do all this kind of projections and variable shuffling and whatever, and I don't have the higher order functions, then it becomes much worse. Okay, and then here I have some tests. So I cannot guarantee that this works, because I implemented it about a half an hour ago, and this is the only test that I wrote for it. so there is a good chance that it's still buggy, but at least this works. So this type is we can actually just print this type out in a nice way. So the type one is, let's do a put strln of, I think we have a short team 0 quote 0 of type 1. Yeah, okay, so this is type 1. So it goes from a sigma of a type. So this is a pointed type. This is called a pointed set in type theory, like a type together with an element, and then we have a function going from the first projection to the first projection. So this is type 1, and then if I do a query, and then you can see that it gets queried. So I get an AU, and then these variable names are not very informative, but it checks out. Okay, and what if I print the tm1? So tm1 is a lambda expression like this, and this is, you can see that this is already queried, so I have to kind of unquery it. So if I do a from query type1 of tm1, then it gets converted to the correct thing. Okay, but and what's the problem with the axiom of choice? So here we can see that this works in a very fine and nice way. So what's the problem with AC? So with AC, I think this is the problem, but maybe someone can correct me. So I think that the problem is that we have to perform some pattern matching under a binder. So we need matching under a binder. And this is kind of a general problem with higher order abstract syntax. Is because the binders are kind of abstract. So here, if I have a C, then the C is a closure, and if I have a B here in the sigma, then the B is also just a closure. So, and usually the only efficient and natural operation which is possible on closures is to apply them to something, and then we get a value. But the problem with the axiom of choice is we have to look inside the closure to see whether it's of some particular form. But after we are looking inside the closure, we have to call the closure with something, and usually the way we do it is that we just get a fresh variable and apply the closure to fresh variable, and then we can look under the closure. But then the problem is that we still have to re-abstract over the body of the closure. And the way to do it is just to normalize the body of the closure and just put it into a new closure. So we have an example for that kind of thing in the context operation. So this is actually this is exactly what I was talking about. That whenever I have a value which is in an extended context, so I have some value which is in extended context, then I can create a closure from it which lives in the non-extended context. So if I have a context and I have a value, then I can create a new closure, but then here I have to perform this quoting. So I can only go from a value to a TM and then put the TM inside some new closure. And this is a very inefficient operation. So because it requires to perform normalization. And this clause in normal elaboration, it comes up when we are doing an inference of lambdas, right? So if I have a lambda expression, then what happens is that I create a fresh meta for the domain, and then I infer something for the t term, but the t is in some extended context. So what I get back, so the b, which is a value, which is the type of t, is also in the extended context, but I have to return a closure, which is this closure for the pi codomain, and then I have to use this close value. And this is really inefficient if we don't have glue evaluation, because then the only reasonable way to go from a value to a term is by doing a full normalization. So this becomes a bit more efficient if you have glue evaluation, because then the quoting can be a lot faster. Okay, and ages, and here we have a similar problem. So here the problem is that in the axiom of choice, I want to do like this AC-ification or this columnization of some AA, arrow BB, and then here I have a C of AB. So B depends on A and C can depend on A and B. And I want this to be, so we can just forget about the recursion involved in this AC-ification or columnization and just do the one-step conversion of AC here. So it becomes a B which goes from AA to BA times AA arrow C of A of B of A. So it becomes this. And you can already see that the problem is that I have to do pattern match on the I have to do a pattern matching on something which is under a closure binding. So the way I can do it is by applying. So here I already have to keep track of the environment. So here in currying I don't have to keep track of the context, but here I have to keep track of the context because I can only go under a closure if I get a fresh variable. So I have to do some, maybe apply a b to a v var of level, and then I can do a pattern matching on this, and then I get a v sigma of some x a b, and then I can do something, but then I will have to use this what was it called, close val. So actually, if we want to do this AC conversion, probably it makes sense to just not implement this operation on values, but instead implement it on terms. But if we want to implement it on terms, then we have to define like this general toolkit of operations on terms. We need either explicit substitutions or an implementation of implicit substitution. So we can still do it efficiently, but we cannot do it efficiently on values anymore. We can probably only do it efficiently on terms. And I think, so this is also related, so related issue is normalization by evaluation for cubical type theory. Because in cubical TT, some computation rules in the core theory require using close val. And that's why if you look at the concrete implementation, so if you look at this kind of cubical TP, then this uses NB only for normal values and uses naive substitution for intervals because of this problem is that some computation, and this computation which involves transports like cubical transports and cubical intervals, it doesn't really work nicely with usual MB values, and then they just use naive substitution instead. But then this naive substitution is also horrible from a performance perspective. So I think it's kind of an open issue. So how can we do an efficient environment machine implementation for cubical computation rules? And in simple cases, like in very, very simple cubical type theories, it can be some kind of worked around, but in the full cubical type theories, I don't know if this can be worked around. Okay, and this was kind of a side topic, but I think it's interesting. Okay, so what else changes? So we still have this fresh meta operation. So fresh meta operation just applies a fresh meta to every bound variable in the context, which is represented with this pruning, which only picks out the bound variables. Okay, and but there is a different version of fresh meta. So there is a fresh expanded meta, and the fresh expanded meta does a recursion on the type. So if the type is a sigma, then we are creating two fresh expanded metas and we return a pair. If you have a pi, then we create a new fresh expanded meta and then we return a lambda. Otherwise, we are returning just a fresh meta. Okay, and there is this function which performs what I mentioned, like this transport over currying additionally on the top of this eta expansion. So here if I have a meta, then this A is the type of the meta. So I look up the type, and then I compute the curried version of A, and then I create an expanded meta with the curried type, and then I solve this old meta with the transport of this expanded new term using this from query of A. Okay, but yeah, and okay, this doesn't change much. So inversion changes a bit. So because now inversion, I have a different kind of exception in inversion. So previously I only had this very stupid kind of blanket exception called unify error. This would be actually nice to, even in this implementation, make it a bit more fine-grained so that we get more informative error messages. So previously we only had this unify error, but now we also have this need expansion exception. So if in the spine we have an application, then we look at the value in the application. If it's a bound var, then we do the usual stuff, like we are kind of checking linearity. and if it's a pair, so here, if it's a pair, then I also throw a need expansion. And now I realize that I should also throw a need expansion on projections. So there should also be a v-flex. Yeah, so there should be all of these kind of cases. So it's the v-flex and the projection of a spine. Sorry, not the v-flex, but the v-rigid. Because if it's a v-flex, then it's completely hopeless, right? Because if I have a meta variable inside the spine, then it's not solvable by pattern unification in any case. So if I have a rigid projection inside the spine, then that can be still corrected by doing this expansion. So a rigid, and then I also draw this, and the same way. Second projection, and also with field projection. Yeah, and I don't even have to mention the spines. No, because it's S for spine. Okay, hopefully this is okay, but we will see. Yeah. Okay, so we can see that if inside an application we have pairs or projections, then this problem needs an expansion. Or if the spine itself contains projections, then we also need an expansion. And then we are using the invert function. So when we are doing this solution, then we try to do an inversion of the spine, and if it needs expansion, then we perform this eta expansion, and then we retry the unification of the same problem. But when we retry this problem, then of course, because an expansion already solves the m, then this m will be solved, and then the left-hand side of the equation is going to be computed to something completely different, because now m is already solved. Okay, and otherwise we just do as usual. So if you have some unify exception, then we just rethrow it, and otherwise we are proceeding with the solution. And let's go back to this eta expand meta. Oh yeah, we already seen this, right? So So I already mentioned what happens here. So here we have this expansion, and we also have this transporting along the currying isomorphism. Okay, and yeah, and I think there is no other interesting change. So there is also, so we also have to handle these projections in unification. So you can see that proj1 can be unified with proj1 and proj2, and with proj field here we need some helper function which can do this kind of unfolding of a field projection to some iterated first or second projections. And we also need to unify sigma with sigma, and we also need to unify pair with pair. However, it is important that we also have an eta support for pairs. So if you look at this part of the code, so previously we had eta for functions, which works like this. So lambda lambda as usual, but if I have a lambda on one side and a non-lambda on the other side, then I can apply to the other side to a fresh variable, and this takes care of the eta conversion checking for functions, and the same thing works with sigmas. So if I have a pair on one side and a non-pair on the other side, or a pair on the other way around, then I can do a projection using vproj1. Okay, and is there any change in elaboration? There is there are some slight changes. So I also have to deal with sigma in checking, but this should be completely obvious. So if I'm checking a pair with a sigma, then I want to check the first field and then the second field of the sigma. And when I'm doing inference, then there are some kind of design choices. And I think the main design choice is what to do when we want to infer a type for a pair. So this is kind of an interesting question, because if you think about it, like what happens if I want to infer a dependent sigma type for a pair expression, like let foo equals tu. So I can try to do it. So this should be the dependent sigma inference. So I could try inferring first a type for t. So I always have to, in any case, I have to infer a type for the first projection. And then I have to do something with the second projection, but the second projection has a dependent type which can depend on t itself. So what I could do is to create a fresh meta. So now I'm not writing correct code, I'm just kind of creating a pseudocode. So if t has type A and B may have type, actually I can just write it because I already have code which looks like this. So if t has type A, then I need to have some type which depends on an additional type. So I can say that I create a fresh meta in an extended context. So I extend the context with x with type A, and then I create a fresh meta, and then I can just immediately close it, because here the fresh meta operation, fortunately, it returns a term. It doesn't return a value. That's why I don't have to use the close val operation. I can just simply create a closure immediately. So I have this b, and then I have to check that u. So I have check in cxt that u has type b applied to the value of t. and then I get this U. And I can return a pure of a pair of T U and also a sigma value of some X and A and B. Okay, so just purely from the perspective of having a correct implementation, this works, but it's almost never usable in practice. It's very rarely works in practice. And why? Because if I have something like a TU, and the problem is that if for example, if I have some meta variables, if some meta variables are involved either in A or B, then the problem is that here this B depends on this bound variable when I create the fresh meta, but I immediately create a closure from it and then I apply the closure to the value of T. So the problem is that if you have some fresh meta and the meta is applied to some arbitrary T, and then T is not a bound var, and I have to solve this, then this is not a pattern unification. So this is not a pattern problem. And the only way that an inference like this ever works with pattern unification is when I'm trying to infer. So I try to infer a type for some X of U, where X is a bound var. So the first projection, usually the first projection has to be a bound variable, because if B is just a meta, so you can see that B is a fresh meta, and if a fresh meta is applied to this eval of T, and this is a bound var, then we get a pattern. But if this is not a bound var, then we do not get a pattern. B must be applied to a bound var. And for example, it works if I write a function like lambda n, which has type not, and then I write some n and maybe some replicate n of whatever, and then I also know that this replicate n whatever, it returns a vector, so the replicate n true has type back bool of n, and when I create this fresh meta, so when I create this beta for the second projection, then the second projection gets applied to n, and then I have to do this kind of solution. And then this works. But usually this does not work, because it's fairly rare that we are writing a bound variable as a first projection. But if you have postponing, so like in Agda, if you have like more sophisticated postponing, so postponing, it can make sense. But I think without postponing, this is just too weak, and instead what I have here is that we are inferring a non-dependent product type for a pair expression. So we just infer one type and the other type, and here this is just a non-dependent function type, and actually I can replace this. So you can see that here I'm using something which looks like a closed val, but actually now, because we have this higher order constructor, it is already possible to do a fun of lambda b. Okay, so this is another use case for this higher order constructor for closures. But the reason that this works, so So this is a very critical thing actually. The reason that it is correct to put a b, so b is a value in gamma, but here I'm using b under an additional binder. And so why is it correct? And the reason is that for values, because we have De Broglie levels, we can always move them into any extended context, because weakening is just completely implicit for values. So this is the reason that we can do this, is because we are using De Broglie levels. Okay, so yeah, and then projections are kind of, yeah, I think probably obvious. So here I have some kind of boilerplate code, because if I am doing projection of T, then I have to ensure that T has type sigma of something. And kind of the efficient way to do this is that I just pattern match on the type, and if it's a sigma, then it's okay. But if it's not a sigma, then I'm just creating a fresh pair of meta variables and unify it with so unify the type with the sigma of a fresh A and B. And the same thing happens with the second projection. So here I also have to ensure that T type is a sigma. And with field projections, probably this is not too interesting, because we are just doing. Okay, actually, this implementation here is not is a bit too weak, because you can see that this pattern matching should ensure that the type is a sigma, but here I am completely skipping the. Oh, I know what's happening here. Okay, so and this is actually a bit interesting. So here, this case of force SG, so SG should be a sigma, and then I'm doing a pattern matching on it. And if it's already a sigma, then it's okay. But if it's not a sigma, then I don't even try to do this unification dance. So if it's not a sigma, I don't even try to do the unification. And why? Because the field projection elaboration depends on exactly having the right name in the sigma binder, right? So I don't try anything, because I cannot get any name to compare this given field name to. So I just drove an error. And in practice, this means that if I'm using a named projection, then it only works if the thing which I'm projecting from already has particular known sigma time. And with postponing, this could be also improved. The inference until type is known. Okay, and let's look at some examples, and I think probably I will have time to talk a bit about generativity of sigma types and record types as well. So let's go to this main file and just do some quick trial runs, because I made some changes in the code and now it is possible that it doesn't work. So what was x2? Oh yes, it's nothing too bad. Yeah, now this works. x3. Okay, it also works. We also have x1. Yeah, we also have x1. Okay. Okay, so let's look at this. So in this example, you can see that I can define category to be So I can define the type of categories to be an iterated sigma type. So I have here an object and a morphism, and an identity and a composition, and now I don't care about the category laws. I could also use this church encoded notion of equality, but for examples it's enough to only have this. And then I can also define the category of sets. And here maybe I could make it a bit less confusing visually, but the rule is that so the way I implemented the syntax here is that everything binds stronger in the syntax than the comma for pairing operation. So I can simply write a U and a lambda and a lambda here, and I don't have to parenthesize these individual components, but this is kind of just a syntactic choice. And then I can also define functors, like the type of functors between categories. And then it's a lambda CD, and here it's nice because I can overload the field names. So I can just call the action of objects to be, I can name the action of objects as obj, and it's a function from c.obj to d.obj, and the projections actually in my syntax also bind stronger than function application, which I think makes a whole lot of sense. So if projection binds stronger than function application, then we can simply write like an x, like a function applied to a c.obj, and then it looks a bit like the usual record projections in languages. So in languages where we have like or the primitive, like this qualification of methods and whatever. So we do not have to parenthesize this because the projection binds stronger than function application. Or we can write f applied to x.1 and y.1.2 and so on, and then this is the same as with parents. Okay, but these design decisions are actually just what I started to use in the setoid type theory prototype. I thought a bit about like what is a nice syntax and what is a nice setup, and I think this is nice, but you can also disagree or or have different ideas how to do this. And we can also, so this is completely type directed. So field projections are completely type directed, and we can just arbitrarily overload all the field projections. Like as we've seen before, if I'm doing a named field projection, it just depends on the sigma type and the name which is given in the sigma type. So if I have some f, which is a functor from C to D, then I can just use f obj of y in order to refer, just to use the action of f on objects. And at the same time, I can use c.obj, and obj is overloaded. Okay, so we have this. And then here I am defining the identity functor, as usual. And here I'm defining the functor composition, and these are some tests for sigma unification. So here this is a test for eta expansion. So I'm declaring a new meta which returns in a pair. So you can see that M has this type, and then it's just defined to be a fresh meta using the whole. And then I want to do an elaboration on this referral, and so I want to unify a projection of mx with x. So here I'm using a lambda to introduce a new bound variable, and then I'm using the church encoded equality type to force a unification problem. And I just want to perform this unification. I'm not yet sure why I need this explicit x in this referral here, but for some reason I need it. Maybe it's a bug, but it's also possible that it's not a bug, it's just a limitation of the current unification. Okay, but this works. And this is a test for currying. And here we can see that the meta depends on a pair, and here I have a unification problem which involves m applied to a pair, but after I perform the currying, then this disappears because m is solved with a curried version. Okay, maybe, but if I comment these out and I look at the elaboration output, then maybe it becomes a bit more readable. So this is x2. And now let's look at the elaboration output. So we have this m test and m prime test prime. And you can see that here everything is filled, so all implicit arguments are filled, and here m is solved with 0. So here this is the eta expansion example, and you can see that m is solved to be the 0, but 0 is solved to be this lambda returning a pair of a bound variable, and here there is a fresh meta variable. So you can see that there was an eta expansion, but only the first projection is solved and the second projection is still unsolved. And in the other case, here you can see that we have m prime which is solved with meta 7. And here you can see that that this is solved with the first projection of the argument. So this is completely solved, and this is the 0 de Bruijn index. Maybe I haven't mentioned, but whenever I do not have any informative name to print, then instead I'm printing a de Bruijn index. So 7 is just solved to be the first projection function. Okay, but let's uncomment just for a bit this code related to categories, and also look at the output that we get. And I think it's interesting because now you can see that it makes a lot of sense to have gluing because we have some like the definition of category and functories everywhere is completely unfolded, and moreover sometimes we also get some eta expansion, so it's already very big and very unreadable. Like all of these types are already kind of starting to explode, so this is a good demonstration of why we need glue evaluation. And another interesting thing is, for example, like what happens if I want to define this ID which just shadows the previous ID. So I say that this is the identity functor, and for every C, which is the category, I get a functor from C to C, and it's just defined to be ID. So this is just a kind of a shadowing definition. There is no recursion involved. This ID just refers to the previous ID and then shadows it. So does this work? And if we try it, then for some reason we get an infinite loop. Okay. I think there is probably some issue with inversion. So when I tried it the last time, it didn't loop, so probably I have a problem here. Let's just delete this and see if it works now. Yeah, it works. I will look at what the problem there is, but I think the problem maybe is that with the shallow kind of currying, I cannot get rid of all of that projections. So it just gets to infinitely try to curry it and expand it, and yeah, so I'm pretty sure that was the problem. I was just kind of a bit too eager to insert all of these cases. Okay, so here what the problem is, and so there is a unification issue, and if you look at this type, then this is just the functor type, right? So this is the functor type which goes from C to C, because we have an action on objects, and then we have an action on morphisms, and then we have a church encoded unit type at the end, because every right nested sigma type must have something on the end. Okay, and we cannot unify this expected type with the inferred type of ID. So for ID we insert two fresh meta variables with type cut. So we have two unknown categories which ID is applied to. So we have this kind of inferred type, and you can already see that we have the currying in action, and this is not very readable. So you can see that this meta variable is actually applied to all of these projections, because the problem is that there is some eta expansion. So this meta variable, it originally only depended on a category, but when it is eta expanded, it depends on all of the components of the category, and I can get the components of the category by using iterated projection, and here we kind of forget the names of the projections, and so this is another point of improvement. So maybe we should also try to remember the named projections when we are doing this eta expansion. Okay, but here what's happening is that so we want to unify this with this, and it's completely fine. So if you look at this, we only have pattern unification problems, it's completely fine. And then we want to unify the type of action on morphisms with the inferred type. And now we just kind of have to squint and try to visually ignore all of these eta expansions, but we still have something which goes from an implicit I and implicit J to a morphism of I, like, and we also have a morphism from I to J, and then we return another morphism, but from an obj of I to an obj of J. So this is like the usual thing in the definition of functors. But if we look at this type, so if we look at this type, which should be unified with this type, here we can see that this is not a pattern unification problem, and this cannot be repaired in any way, because this is a spine, and the spine contains a function application, like an application to a function application expression. So what does this mean? So this means is that actually functor is a cut arrow Q definition, and functor is not injective up to definitional equality, or it is not injective up to unification. So if I have a functor of CD, so I have a unification problem, like is a functor CD equal to a functor CD prime, and if this succeeds, then does this imply that C is definitionally C prime and D is definitionally D prime? And actually it doesn't. But in Agda we get this. So in Agda records are primitive. So the record type constructors are injective I mean, not internally injective, but the unification algorithm sees them as injective. So they are injective with respect to unification. And here they are not. And this is a pretty big problem. So now this boils down to this like injectivity or generativity of record types, and also in general of derived type formers. So this problem appears if we say that record types are not primitive, but record types are instead derived from sigma types. And similarly, we can have a very similar problem when we say that inductive types are derived from, for example, like codes or some kind of generic scheme. Inductive type formers are derived from some kind of generic scheme. Then we have the same generativity problem. And what's the solution? So one solution is just to not have this and say that all of these types are primitive. But I think that's kind of ugly. So I think there is a real reason that records should actually be just iterative sigma type. It's definitely it's more flexible, and it's more convenient, and it's also a bit more elegant in the internals of evaluation and elaboration. And I think it's not necessarily much slower, because if you have a system which is implemented properly and which is already fast enough, that it doesn't make a lot of difference to say that we are just nesting all of these sigma types and all these pair constructors, because I think it's fast enough. So I think that it's a good idea to have this kind of generic stuff, but we have to fix the user experience. So how can we fix the user experience? And my proposal is to have kind of user injectivity annotations on definitions. But these user injectivity annotations on definitions, they are not they do not change definitional equality at all. So they are only relevant to as kind of a only relevant as a convenience feature in elaboration. But they do not actually change the internal notion of conversion. So in Agda, the conversion is actually it's changed if we have a sigma type instead of a record type. But here I say that I only want to have something which behaves like the Agda record type when the unification machinery wants to infer something. But when we have to compare some record type to some sigma type, which is not obviously the same because it's not the same name, then we still have the convertibility between the definition. So we still have a convertibility, for example, between a functor as a name and the unfolding a functor to some particular sigma type. So I say that we should be able to do something like maybe, or I say that there is a let, and then there is some kind of attribute or some kind of meta tag on the let definition, and then I say that let generative category equals blah blah blah. And then in unification, if I have to compare, so okay, see you. So in unification, if I have to compare like category with category. Okay, maybe a category is not interesting, but functor is a bit more interesting. So a functor goes from cut u equals blah blah blah. So in unification, whenever it comes up that I have to compare a functor CD with a functor C prime D prime, then I just do a unification of C prime and D prime. And whenever I have a functor CD equal to something else, then I just unfold functor. And if I have some machinery for glue devaluation, then it is possible to slightly enhance this glue devaluation to give the opportunity to do this. And then what happens is that I still get some nice inference behavior which works like Agda, but of course if I'm doing this, then it loses some solutions. So because functor is actually not injective up to definitional equality, so this loses unification solutions, but we don't care because it is just more convenient to have a generative functor. So it loses unification solutions, but it's still complete with respect to the usual conversion checking. So complete conversion. And I think this is probably a good solution. And it should be also possible to extend this system, so there should be an injectivity analysis which kind of inserts these generative tags whenever some binding is actually injective up to definitional equality. And then we can use it for optimization purposes. So we have this injectivity analysis, and then we still get this shortcut. And if something is actually injective, then this just does not lose any unification solutions. So by supporting this kind of generativity annotations, then we can also support some additional optimizations on the top of this.
Can you be a bit more concrete about what solution do you lose? Like, can you show for this functor example, for example?
Oh, I'm not sure, because it's already a bit complicated. But if we can just try to copy this, so you can see that I want to unify the C.Mor with. I can also try to make this a bit shorter, so I want to unify this with some. Let's put the meta variable on the left hand side. So obj y, obj j. Yeah, so I think this is the problem. That I have some meta, and then I know that if the meta is applied to these things, then it should be equal to C.Mor. And but C.Mor is not necessarily an injective function. It's just a yeah. I mean, so obj is just an arbitrary function which comes as a bound, like obj is kind of a bound variable, and C.Mor is also it's a projection of a bound variable. And the problem is that here we have this in spine, and okay, but maybe you can say that, like, could we solve this as lambda xy dot c dot more xy. In this case, the solution is well type, right? So actually, the solution which we would like to see here is just that alpha is equal to c dot more, right?
Yes.
But this is not a pattern problem. So I could also have for example, this as a solution. So I could have like right? So this is also well typed, and this is a different solution.
Mm-hmm.
And so the problem is that the a functor has this. So the action on object appears in the types, and because the action on object is just an arbitrary function, then this does not uniquely determine the category. It actually, if you look at it, it only determines the category which is the image of the functor.
Mm-hmm.
Yeah, so it only determines the object which are in the image of the functor.
Mm-hmm.
Okay, I think this is it for today. Time's over. So yeah, so I wanted to figure out the implementation of this full expansion with not just with currying but also with axiom of choice. Maybe it can be a homework. So, but I also want to look at it because I only started to work on it yesterday, and I figured it out yesterday and this morning because I haven't implemented this before, and I think this currying is just very, very simple and nice, but I would like to have some nice solution for the axiom of choice as well. So if you go back to the notes and just look at this formalization, then yeah, I mean it's possible. We are just doing some syntactic model and such that actually everything is converted to an isomorphic thing, and we can just repeat this in Haskell. But if we just repeat this as it is, then we have to use either explicit substitutions or an implicit substitution on terms. And maybe this is actually the right solution. Okay. Any questions or comments?
Could you do those things solving the meta variable? So handling currying and the axiom of choice with a broader pattern condition, you would say, or a pattern condition that covers those things as well. Makes sense.
Yeah, so there is some paper about this. So here I mentioned I mentioned that there is some existing work, and I think it's a reference from maybe this higher order unification paper as well, but I haven't read it. And so I spent a little bit of time just trying to figure it out, like how it would work. So if I have some, like for example, if I do an x1 and y1 equals maybe x1 arrow y1. So naively we can start to think about how this should work. So in this case, so one naive algorithm would be to say that projection of a bound variable just behaves as a bound variable. So it will be like a projection of bound var is like a bound var. And then the solution would be right, so yeah, and I'm not sure, so I only spent a little time thinking about this, and maybe it works, but I think it would end up very much like the other solution. Maybe it could be a bit more efficient, because maybe here it works even if we don't look at the type of 0. So if we are doing this full eta expansion and currying and sigma elimination, then we have to look at the types. But maybe if we are only looking syntactically at these projections, then it's more efficient. But I don't know. But it's a good topic.
Thanks.
And then we also have like and here we say that if there is a bound variable inside the pair, then it becomes a projection in the solution, so it becomes like maybe that one arrow, maybe that two, or whatever. But I mean, on first look, this does not seem to be simpler. It could be, it's probably exactly as complicated as the other solution, but it could be more efficient. I'm not sure.
Another thought that I had was pairs. Would it be worth adding a special case for inferring pairs that start with a variable?
So inferring pairs we start with the variable, so it was an elaboration. Right, so yes. So we can just do it. So we say that we are inferring right. So if the pair has a variable, then we try to do the dependent version, and otherwise we try to do the non-dependent version here, right? But then we still have to, it only works if this is not a let defined thing, but a bound thing, but I get the idea. And probably if you have postponing, then we don't have to include the special cases, because everything should just work. Okay, so let's end the recording.